This is AP Calculus 6-2, approximating areas with Riemann sums. And we have introduced what integrals mean. And integrals are basically the area underneath the curve. And we talked about when we have the area underneath the curve, we're actually talking about the area between the curve itself and the x-axis. And then we also have boundaries of the portion of the f of x function that we are trying to find the area of, and I'm going to let my boundaries be a and b. So dealing with integrals and understanding what they mean is something that we need to explore a little bit in this section. And we're going to be talking about finding Riemann sums with rectangles, and the idea is that if we separate this portion of what I'm trying to find the area of into smaller and smaller and smaller rectangles, we will be able to find an area approximation that is closer and closer to the actual area under the curve. And let me show you what I mean by that. Now, our notation is still the same. We said that the integral symbol on the interval a to b of f of x, d of x. And we kind of hinted in the last section that this d of x represents the thickness of the rectangle. We're going to talk about how that affects everything when we're dealing with finding the area under the curve today. And when you're dealing with Riemann sums, they're going to say find the area under the curve using a left Riemann sum or a right Riemann sum, or using trapezoids, or by using the midpoint rule. There are 4 different rules that we're going to be dealing with in this section. And I'm going to start with your left and right Riemann sums first. All 4 of those methods are finding the same thing, the estimated area under the curve within a specific interval. But they all do it a little bit differently. Some more accurate than others, but I think as we work through this and you understand how this works, it's going to give you more of an understanding of where we're going. How does this pertain to calculus? Well, the first chapter we did in calculus was on limits. And basically what we're showing here is that as your rectangles get smaller and smaller and smaller, then the limit of our answer is getting closer and closer and closer to the real area underneath the curve. And I'm going to start with left Riemann sums, and then we'll compare that to a right Riemann sum. And basically what they're going to do at first is they're going to say, separate this into 4 rectangles and estimate the area under the curve. So I've tried to separate the area from A to B into 4 rectangles that have the same width. Okay, well, as we do these, we're going to make our rectangles have the same width. Now, as we move through calculus, they're not necessarily always going to be the same width to be able to estimate an area. But to start us out, that's what we're going to do. And you can see that these widths of these rectangles are about the same. The widths of the rectangles are going to be considered our dx. The thickness of the rectangle, or our width of the rectangle, is dx. And the idea is as dx gets smaller and smaller and smaller, the area under the curve is getting closer and closer to the actual area. Now, what I'm going to do for the left Riemann sum is, and remember, this right here is not one of our rectangles. That is the portion that we're not talking about. I'm going to put an X there to understand that's not part of what we're talking about. We're talking about the area from A to B. This is the portion before that. So we're finding the area of the curve from A to B. Now, if I'm going to do left Riemann sums, what I'm going to do is I'm going to draw rectangles from the left part, or from the left side of each rectangle, over until it touches the other rectangle. So I'm going to go up to the graph right here, and I'm going to draw straight over to form a rectangle. I'm going to go to the next rectangle. From where it touches the f of x graph, I'm going to draw another rectangle to finish that rectangle out. From the point where the left of the third rectangle is, I'm going to draw another rectangle. And then from the point that the 4th rectangle starts, I'm going to draw another rectangle. We have drawn our rectangles from the left, and this would represent the left Riemann sum. Now, if you think about this, in this rectangle, we're not accounting for the portion of the area that's underneath the curve right here. In this rectangle, we're accounting for more than what is underneath the curve. In this one, we're accounting for more again, and for this one, we're accounting for less. And the idea is that this part and this part, and they're close to the same amount. So this one's over and this one's under, so it's going to get us something close to the actual area. This one here is over, this one is under, so again, they're going to kind of cancel each other out. Now it looks like this is a little bit bigger than this one. So I would guess that this is going to be an overestimate. And sometimes they're going to ask you when you're dealing with your problem, is it an overestimate or an underestimate? And basically to find the answer to this, when we're separating this into 4 rectangles with the same width, to find the area under the curve, or to estimate the area under the curve, we're going to find the areas of each of these rectangles and add them together. That would be our approximation for the actual area under the curve. So to figure out the area of these rectangles, if you think about it, we're going to know the distance from A to B. Like this distance might be from 1 to 5, okay? Well, if this is from 1 to 5, then we know the width of each of these rectangles is going to be 1, okay? And then the height of the rectangle, well, when we're doing this for real, they're going to give us a function for f of x. So isn't the length from the x-axis up to the point on the curve, isn't that going to be a f of x? If we plug a into the function, won't we get the height of our rectangle? So we're going to have the width and we're going to know the height by plugging into the formula. And then if we multiply the width times the height, we'll get an area for that rectangle. This width is going to be the same as this width. All of the widths are going to be the same. To get the height, we would plug the number. So like if this a is 1 and this ends up being 2, then we would plug 2 into f of x and figure out what the height is, because the height of each rectangle is your y value where it touches the function itself. And so when we find the area of these rectangles and add them together, we now have an estimate for the area under the curve. It's going to be a little bit higher than what the actual answer is, but it's a good estimate. All right, they might ask you, instead of separating this into 4 equal rectangles or rectangles of equal width, they might say separate it into 8 rectangles of equal width. So I'm going to do that. I'm going to get rid of my lines here. So I've gotten rid of the lines. I now want to do 8 rectangles that have equal width. So I'm going to draw a line up halfway between each of the existing lines. So now if I want this to be the left Riemann sum again, I'm going to draw my lines from the left until they touch the rectangle length on the right. So if I do that, I'm going to have a rectangle here. From this point, I have that rectangle. From this point, I have another rectangle. And I continue this pattern until I have drawn all 8 of the rectangles. And so you can see here, this rectangle has a little bit of area that we're not accounting for. This one looks pretty close to what it actually would be. This one has a little extra. Those two look like they both have about the same amount of extra. So they're going to cancel each other out. These two both have a little extra. This one has a little, it's almost exact. This one has a little bit less than it needs, and this has a little bit less than it needs. So you can see that by separating this into 8 rectangles, the area of the curve is getting closer to what the actual area would be. I could then do this again. I could go draw another one between each of these and do 16 rectangles, and it's going to be even closer to what the actual area is. And the idea is, as dx, as the thickness of the rectangle gets closer and closer and closer to 0, the area under the curve gets closer and closer and closer to its actual area. So that's a left Riemann sum, drawing from the left. If I wanted to do a right Riemann sum, I'm just going to get rid of the tops of these rectangles so that you can see what happens with a right Riemann sum. The difference is, if I'm drawing a right Riemann sum, instead of starting my rectangle on the left, I'm going to start them on the right. So I'm going to use this point and draw my rectangle. So here I've drawn my 8 rectangles using right Riemann sums. I've gone from the right to the left and drawn my rectangles. Okay, so a right Riemann sum, we start on the right and go to the left. So now, if I wanted to find the height of this rectangle, wouldn't I plug b into the f of x to figure out what this length is, what my y length is to go up to my curve. And I start on the right and draw my rectangles to the left. They will tell you how many rectangles they want you to separate this thing into, and then you will have to figure out the distance for the width of each rectangle, and then you'll plug into the function at each of these x values to find the height of each rectangle. And the more rectangles we do underneath the curve, the more accurate our area under the curve is going to be. And sometimes they will ask you if this is an overestimate or an underestimate, and you will be able to tell based on the way you have drawn the rectangles. And I'm going to show you some more pictures of these that are computer generated. It's not real easy to draw these on our own, but if we see some computer generated pictures, it's going to be a lot easier for you to tell whether they're overestimates or underestimates. So for today, we're just doing left Riemann sums. In the next lesson, we'll do right Riemann sums. In the next lesson, we'll do midpoint rule, and in the following lesson after that, the trapezoid rule, and all of them are very similar. So the first thing we need to understand about left and right Riemann sums is how to draw them, or how they look in the graphs. Here's a picture of a left Riemann sum and a right Riemann sum. You see in red we've got a function. We'll just call it f of x. And then for the left Riemann sum, what we're going to do, they'll tell us how many intervals they want, and usually the intervals, if they give us the function, are going to be equal distance from each other. So here we've got 8 subintervals going from the left to the right. So if I put dots on the function, the left Riemann sum would be the sum of all of the rectangles that we get as we draw those rectangles from the left of the dots or of the ordered pairs on the graph. So we would draw the rectangles from the left where they are on your f of x. It's easier to see up here because they're not so close to the red function. For the right Riemann sum, if we're drawing from the right, you can see that the rectangles are drawn from the right, then down to the function. So wherever the right end of the rectangle would be showing up on the function itself, we draw the rectangle toward the left. So from the right to the left for the right Riemann sum, from the left to the right for the left Riemann sum. Here's another example. This one is the left Riemann sum, drawing from the left. And notice we're going to have some excess here. That would be an overestimate because we're getting some extra area where it's to the right of the blue f of x function. This one right here is the right Riemann sum, and you can see that's an underestimate because we're leaving out some of the area underneath the curve. This one is the midpoint rule, which is what we're going to talk about in the next video. The midpoint rule goes halfway between your intervals to draw the rectangle. So part of it will be inside, part of it will be outside of that f of x function. Here are those three again. Here's your left Riemann sum, starting from the left to draw. This one is the right Riemann sum, drawing from the right. This one is the midpoint, which we would start in the middle of the two endpoints. So we'll talk about that in the next video. When you're dealing with Riemann sums, you're not always going to have a function that is all above the x-axis like the previous examples. This one, part of it is above, part of it is below. So when we do the left Riemann sum, some of them are going to be overestimates and some of them will be underestimates, just depending on what happens with the graph within the intervals that we're talking about. So if you look at this one, another thing we need to understand is how to talk about or how to write our integrals for this. This one is going from -3 to 9. So my integral, the interval goes from -3 to 9. If I call the curve my f of x, I would have the integral going from -3 to 9 of f of x. And then remember, the thickness of each rectangle is called dx. So that would be the notation for the area under the curve from -3 to 9. Now, we're not going to get a real accurate area here because we're going to have part of it being an overestimate, part of it being an underestimate. We'll be fairly close to what the exact answer is, but it's not going to be perfect. We're going to take this example. It says estimate the area bounded by the curve and the x-axis on the given interval using the indicated number of subintervals by finding A, the left Riemann sum,
B, the right Riemann sum, C, the midpoint Riemann sum, and D, the trapezoid rule. And we're going to use the function y equals square root of x on the closed interval from 0 to 1, and we're going to subdivide it into 4 sub-intervals. And those sub-intervals are going to be of equal width. So we're going to take this to the whiteboard, and in today's video we're going to do the left Riemann sum. The next video we do will be the right Riemann sum, the midpoint Riemann sum, and the last video, or the video after that, will be on the trapezoid rule and finding the area under the curve. And you'll see how all of these Riemann sums relate to each other over the next several days.
So I've taken the information from the problem, y equals the square root of x, and we're looking at the subinterval, or we're looking at the interval from 0 to 1, and we're going to separate that into 4 subintervals and find the left Riemann sum. So the first thing you're going to have to do is find the graph, because we're going to have to find the length and the widths of the rectangles that we're going to end up finding. And if you think about what the square root of x function looks like, you should have learned that in Algebra 2 probably. The basic shape of a square root function looks like that. And we're only talking about the square root function from 0 to 1. So we know if we plug 0 in, we're going to have the point 0, 0. And if we say, let's say this is 1, and let's say this is 1, if we plug 1 into that, we're also going to have 1. Now, we could plug in other numbers here if we wanted to, and we would see that the function does follow along that curve. So I'm just going to make this real simple. I know what the basic shape of a square root function is, so I'm just going to draw it in there. It doesn't have to be fancy, it doesn't have to be exact, you just have to know the basic shape of that, because we're going to use the equation to find the lengths of the heights, I should say, of the rectangles. So they have told us to find the left Riemann sum using 4 subintervals. So if I use 4 subintervals, this one is 0. I need 4 equal intervals between 0 and 1. So I'm just going to draw up from 1. There's my right end of my shape. I'm going to go halfway, so that would be at the 1/2 mark, and then I'm going to make marks halfway between each of those. So this would be at 3/4, this would be at 1/4, and I'm just going to draw lines straight up to my graph from those points. So I've got one there, and again, this does not have to be drawn to scale, you just need something that looks close. And then we're asked to find the left Riemann sum. So that means I'm going to draw my lines from the left on the function to the right until I touch the other side of the rectangle. So from the left, I'm going to start at 0, 0, and I draw the line to the curve there. So that first rectangle is not going to yield any answers. It's not going to give us any area there at all. The second one, I start here and go from the left to the right until I hit the other side of the rectangle. The next one starts here, and the last one starts here. Now, if they were to ask you if this is an over or an underestimate, I would say it's an underestimate. First of all, you don't have any area here because of the way we had to draw the line. This area of this rectangle is well below. We've got this leftover part, this one a little less leftover, and this one a little less leftover still, but we still have an underestimate because we're not going to be accounting for this whole section, this, or this section. So this is going to be an underestimate. And then all I have to do from here is I have to figure out, well, we know that the width of all 4 of these rectangles is 1/4. So we know the width of each of the rectangles. We have to figure out the height of them. Well, this height is 0. So for my first rectangle, I'm going to have the width, 1/4, times the height, which is 0. For the second rectangle, this one right here, the width is, again, 1/4. The height is this height right here. So what would I get when I plug 1/4 into the square root of x? And that would be 1/2. So that would be, for that rectangle, 1/4 times 1/2. For this rectangle, again, the width is 1/4. The height would be what I get when I plug 1/2 in. Well, that would be 1 over the square root of 2. And then the last one, the width again is 1/4. And when I plug 3/4 in, I would get the square root of 3 over 2. So I could put that in my calculator. I know I have 0 plus 1/8 plus 1 over 4 square root of 2 plus square root of 3 over 8. And they're going to ask you to round these to a certain decimal place most of the time. So it's okay to use your calculator for this. And I end up with 0.518 as my area under the curve using 4 subintervals, doing the left Riemann sum.
Sometimes, instead of having to draw the graph like we did on the whiteboard, they're going to give you the graph and just ask you to estimate the right Riemann, left Riemann, midpoint, and trapezoid rule. And so when they give you the graph, it makes it very simple. It's a very simple process. In this video, we're going to do the left Riemann sum. So for the left Riemann sum, I'm going to draw rectangles from the left toward the right and estimate the sum of the areas of all of those rectangles. So I've drawn the rectangles using the left Riemann sum. We need to understand that our widths for each of these rectangles are the same. This width is 1. So if you consider the widths of each of these rectangles, the widths are all going to be 1. Their heights are going to be different. And so if we talk about the heights, since this is a left Riemann sum, the height of each rectangle is going to be what the function is at the left part. So if we put 1 in to the function, we should get 2 because that's what the y value is in the graph. So I'm going to put the heights of each of these rectangles in so that we can see what our total area would be. So if you consider the areas of these 5 rectangles, the width for this one would be 1 times the height, 2. This one would be 1 times the height, 3. 1 times the height, 4. 1 times the height, 3. And 1 times the height, 2. So we would end up with 14 square units for this estimated area under the curve using the left Riemann sum. Another thing you're going to see quite often with these type of Riemann sums is they will give you a table of values instead of actually giving you the function for the values. If they give you the function, you just graph the function, separate it into the number of subintervals they ask you to, and then go from there. But if they give you a table, you will sometimes be asked to graph the table, sometimes not, but then they'll ask you to separate the information in the table into either left Riemann sums, right Riemann sums. They might ask you to do the midpoint rule or the trapezoid rule, and you'll use the information that they give you. So on this one, it says, oil is leaking out of the tank. The rate of flow is measured every 2 hours for a 12-hour period, and the data is listed in the table below. The time in hours goes from 0 to 12. The rate, which is gallons per hour, that is the amount of oil leaking out of the tank, goes from, well, 40 to 8. And we can see here that we're going to be able to graph those ordered pairs pretty easily. It says A, draw a possible graph for the data given in the table. B, estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding a left Riemann sum with 3 equal subintervals. C, estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding a right Riemann sum with 3 equal subintervals. D, estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding a midpoint Riemann sum with 3 equal subintervals. And E, estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding the trapezoid sum with 3 equal subintervals. So we're going to do A, we're going to draw the graph. We're going to do B, the left Riemann sum. So the first thing I'm going to do is graph that function. So here's a little graph of what we're dealing with here. And we need to draw the lengths from each of these up to the ordered pair associated with it. So we've got the picture here for part A, and then in part B it says estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding the left Riemann sum with 3 equal subintervals. You need to pay close attention to what this says, 3 equal subintervals, because if you aren't careful, you might think that this is asking you to find it in 6 subintervals, but it does say 3 subintervals. So you have to be real careful and make sure you're following their directions. I think what I'm going to do is show you both of them. We're going to do 3 first, And then I'm going to show you what it would look like if you did do all 6, just so that you can use that as a reference and have one more example. Because there's nothing wrong, it would be just as easy to find 6 subintervals as it would for 3 here. So we'll just do both. But first I'm going to do the 3 subintervals that they asked for. So here are the 3 rectangles using the 3 subintervals. Notice the width of each of these rectangles is going to be 4. To get the area of this rectangle, we're going to use the width of 4 and the height of the rectangle, which would be at 40. So for the first rectangle, the area is 4 times 40, plus the area of the second rectangle. The base is 4, the height, and that would be what it is at 4, would be 36. So we've got 4 times 36. Plus, for the third rectangle, the length or the width is 4 and the height or length, so width is 4, length, what did we have at 8? Well, at 8 it's at 26, so 4 times 26. And then I would use my calculator to figure out what that is. And that gives me 408, and that would be gallons per hour times hours or gallons. In the first 12 hours, the tank had leaked 408 gallons using 3 subintervals. Now, I'm going to do all 6 subintervals next because they did give me enough information to do that. So you could also be a little bit more accurate if you drew 6 rectangles instead of 3. So we'll do that in the next example. And notice I'm taking the line from where it touches the function, then going down to form my rectangles. So you can see all of these going from the left are going to be over estimates. Okay, so if we're talking about the area of each of these triangles, let's just put the areas in here. This width is 2. In fact, all of the widths are going to be 2. And then the height is going to be where we are on the rectangle. So this is going to be 2 times 40, so this rectangle will be 80. This one will be 2 times, at 2 we are at 38, so 2 times 38 is going to be 76. 2 times at 4 we were at 36, 2 times 36 is 72. 2 times at 6 we were at 30, so 2 times 30 is 60. At 8 we were at 26, 2 times 26 is 52. At 10, we were at 18, and 2 times 18 is 36. So if we add all of these areas together, we will get the area under the curve. We end up getting 376. Remember in the last section, we talked about finding the units. We said to find the number of units we're talking about, we would take the units for the y values times the unit for the x values. So gallons per hour times hours. The number of hours cancels, so this is going to be 376 gallons. So the tank, I believe it was asking us how much oil has leaked from the tank in that 12-hour period, and our estimate will be 376 gallons.